Sir,
Yes.
Sir, shall we wait for 1 or 2 more minutes, or shall we?
Yeah, no worries. I can.
Oh, okay, sir. Sir, we'll begin with the introduction. By the time other people will join. Is that right?
Yeah, it's fine.
Okay. So I welcome you all to this national webinar on transmission electron microscopy, organized by Material Advantage IIT Kanpur during the membership drive that is going on. And I would like to introduce the speaker for today's talk, Dr. Niraj Chawake. Thank you, sir, for joining and accepting our request for conducting this webinar. Dr. Niraj Chawake is currently working as an assistant professor at Department of Material Science and Engineering, IIT Kanpur. Before joining IIT Kanpur, he worked as a postdoctoral researcher at Eric Schmidt Institute of Material Science, Austria. He received his BTech in Metallurgical and Materials Engineering from VNIT Nagpur and integrated MTech PhD from IIT Madras. His research is focused on fundamental and applied studies in processing and properties of material system, high temperature structural applications, along with studies about the processing of materials using civil plastic deformation, in situ deformation studies using TEM and synchrotron X-rays, and studies to investigate the effect of microstructure and composition on the deformation behavior of alloys. So it's over to you. Thank you for joining. And
yeah, so should I start?
Yes, sir.
So good afternoon all. Let me thank Shruti, Professor Balani and Materials Advantage team for giving me this opportunity. I also thank Sarvesh who asked me to present my thoughts on TEM. And I also thank you for joining with us in this Saturday afternoon. So let me go ahead. So there is some philosophy which I would like to tell when we talk about TEM. Okay, the first thing is like seeing is believing. So if you see something, you have to believe it. That's what it is. Second is when you see something, it may not be the reality. It may be true, but that may not be the reality. And third thing which I like most is it's not the perfection, but flaws in human beings make them interesting. Likewise, defects in materials make them interesting. So we'll be going to deal about defects in materials in today's talk, and we'll see how beautiful they are. So first of all, let me acknowledge few people. Professor M. Sundaraman, who taught me basics of TEM in my IITM days. Then Dr. Christoph Gama, Mrs. Kanchanwala, from whom I learned to operate TEM. Professor S. Shankaran, Professor A.S. Gandhi, and Professor G. Kumar. In today's talk, I haven't mentioned any references on any slides, but you can refer all these books from which I have taken most of the images. So this is one of the good book from Eddington, which is like practical electron microscopy, and you will get almost what you need for your microstructural analysis through TM in this book. Williams and Carter this is unavoidable book, and you should read this for anything. Hovey and Fultz is a compact book, and you'll find it useful when you want to deal with mathematical analysis in TM. So let me go ahead, and I can summarize TM in this one slide itself. So let me give you an example. You would have done this funny business where you try to create images when there is a power cut, and you put your hands in front of candlelight and you get some image. So here I have used a camera light, and so here is a hand and here is an image which has formed. Now what I do is that I just bring that hand somewhat closer to the light source, and you can see that the image has magnified. So I just moving my hand closer to the light source, I can increase the magnification, and that's what happens in TEM. In TM, it's more complicated. Okay, so here I made this image like it looks like a deer in image form, but actually it's a hand. You know it already. But when you look at TM images, you may not be aware what is sample actually looks like. So here, is it a deer or something else, or is it a hand? How will you figure it out? In TM, it comes handy with a diffraction. So here, I would like to give an analogy. Here, it's an X-ray. So if I know the bone structure or internal structure, I can clearly say that it's not a deer, but it's a hand. But image looks like a deer. So in TEM, these things happens. So you get confused with TEM images, but diffraction comes handy. Moreover, one important point I would like to tell that here we are seeing a transmission thing. So the tilt of sample, if I tilt my hand in a different way, I'll create another images, both in transmission image or in a diffraction mode. So it is very important to have proper tilt of your sample with respect to your electron beam. So how seeing happens? We have seen that here is an object, and let's consider this a light source. This light source falls on this object and it reflects back and it comes to a sensor and we can see it. So this is how in general seeing happens. Let me come quickly to a transmission mode. So you would have seen light microscope where you have source, I call it as an illumination. Then you have a lens assembly like condenser, objective, and here the specimen, and here you have an imaging system. So to say that I have a wave source and then I have a sample which I have placed. This wave falls on the sample and interacts with the sample and creates some contrast, and that is being imaged at this end. And in between you have a focusing assembly. And this is what happens in all microscope. Why I have given a light microscope example, because TM assembly is more or less similar to light microscope. So here there's a first microscope which was developed by Max Knoll and Ruska, and you can see that Ruska won 1986 Nobel Prize, and Knoll didn't get because he was not alive by that time. So it's important that you should keep track of your health and keep healthy and live longer life to get a Nobel Prize. So with this, what is present a microscope looks like. So here is an assembly of all parts, and you have a gun, which is an illumination source or wave source. Then you have some lenses, condenser lenses, which condenses electron beam on your sample, and you have objective lens. Here I have put my sample here, and here there are projector lens, which makes image on this screen. So you have different detectors which are attached, and this we cannot see electrons by our eyes, so we use phosphor screen or camera for recording images. This is how a typical transmission electron microscope looks like. Now, there are some terminologies which I would like to introduce to you. These are brightness. So brightness, nothing but an overall intensity. If I increase the intensity of these pixels here, that will cause an increase in the brightness. And then now there is another term which we use as a contrast, and we'll be dealing with this contrast more frequently in this talk today. So contrast is nothing but differences in intensity. There are some terms like resolution, that is to see fine details, and magnification, that means to see it bigger. So to explain it to you, here you can see the nose of this dog, and here it has a proper resolution here at this end also. But in this case, what I'm doing is here, I'm just increasing a magnification. I'm just blowing off this image, but I'm not seeing any fine details on its nose. So there is a difference between resolution and magnification. So if you try to increase magnification, most of the time, all microscope, the resolution gets lost. So there is a fine balance between resolution and magnification you have to take care. So all these things were developed by Ernst Abbe, and you can see Abbe's theory for image formation. He has given principles of microscopy. He worked with Carl Zeiss. It's one of the leading company to make microscopes, and he's the one who designed the objective lens. So with this, let me come to some important aspect when I talk about electron microscope. So let's understand how electron matter interaction happens first. So there is a term scattering, you have heard this. So I have an object, or let's say an atom here, and I radiate with some electron here, and this electron will get scattered. This will get scattered in different direction. So here I have shown this electron can get scattered in the forward direction as well as in the backward direction, or at any angle. So this is not an intensity, this is a probability of scattering, which I have shown with the magnitude of these arrows. If this arrow is bigger, that means the probability of scattering in the forward direction is higher as compared to the probability of scattering in the backward direction. So scattering is a phenomena which leads to diffraction, and it is only a phenomena which helps us to create a contrast. We'll be looking at it shortly. So here I have scattering, and let's say I have energy of this electron, and it's scattered with an energy E2. Now, when I talk about elastic scattering, that means this energy of incident electron is equal to the energy of scattered electron. So there will be no loss of energy. So when I talk about elastic scattering, what I mean is that delta E is equal to 0. Another thing that now you would have already guessed, if there is an elastic scattering, there must be an inelastic scattering. And you can find that this energy of scattered electron is lower than the energy of incident electron. So there is a loss of energy here. In this process, there is a loss of energy, and that kind of scattering is called as inelastic scattering, where delta E is not equal to 0. So we'll be looking at, or we'll be dealing with these terms as we go on and try to understand theories which explains the image formation in TEM. Now, another scattering, which are where I have considered electron as a wave nature, and it interacts with a material or a matter, and there is no change in its wave or phase. And this is called as coherent scattering. So when there is no change in phase and the wavelength remains fixed, such kind of scattering is called as a coherent scattering. And when you have matter and this wave again interacts, but there is a change in phase or its wavelength, or there is no one-to-one correspondence between incident electron wave nature and the scattered wave nature. That kind of scattering is called as incoherent scattering. And incoherent scattering are mostly inelastic scattering. So we'll be looking at incoherent and coherent scattering also when we try to understand image formation in TEM. Now let's understand electron matter interaction. We have seen scattering. So we have an electron which is falling on the sample, which interacts and creates a lot of signals. So we have backscattered electrons, secondary electrons, X-rays, cathodoluminescence. Then there is a specimen current, and in forward direction, we have elastically scattered electrons, transmitted electrons, and inelastically scattered electrons. We have seen elastically scattered electrons means there is no change in energy, and inelastically scattered electrons means there is a loss of energy. And there is some transmitted electrons. So these are also has the same energy of a primary electrons. We'll not look at this because we are talking about TEM today. So all these backscattered and secondary electrons are useful when we try to understand scanning electron microscope or SEM images. In transmission mode, we'll be looking at only elastically scattered, transmitted electrons and inelastically scattered electrons. Now let's see that we have this electron beam which is falling on your sample, and the sample is very thin. So when it interacts with this specimen, there is a change in intensity. Here you have a uniform intensity, but as this beam interacts with sample, there is a change in the intensity. And this varying intensity only creates a contrast, which helps us to form image in TEM. And why this intensity varies? Because when this electron beam interacts with this thin specimen, it causes a diffraction. The scattering which becomes coherent to each other and thus create a diffraction pattern. Also, there are some forward scattered electrons. So this transmitted or this incident electron beam has some intensity which get lost in terms of a diffraction and some other signals such as elastically and elastically scattered electrons. So this forms a basis for TEM imaging. Now let me move ahead and let us discuss about some schematic ray diagram for TEM. So here I haven't shown something from the gun or like illumination source. So let's consider this here, the top part is an illumination source. And here we have put specimen in this part. And here till we have intermediate lens, we have objective lens. So this part in TEM is almost fixed. We don't alter these parts in TEM. So what we can play with is the intermediate lens. So we provide an electric current which creates a magnetic field around these lenses and thus can help us to diverge that can help us to converge these electron beams to form an image. So this part, this assembly is fixed, and you can see when I change this strength, I can make that there is these spots can be imaged here. These spots are called as diffraction spots here. So I can create this spot just by changing the strength of this intermediate lens. Similarly, I can form an image rather than forming a diffraction pattern. I can form an image by just diverging it more, this beams in this way, and thus it can create a final image. So we can get both diffraction pattern as well as an image in TEM just by changing a current flowing through intermediate lens. So we have an incident probe, we have electrons, and you see that when I have a lambda, which is much smaller, when I use 200 keV electron volts, so it is like 0.0025 nanometers. And how does it help? It helps in the depth of field and depth of focus. That means my sample can be more or less focused. Depth of field and depth of focus helps us to make your sample focused in TEM because of this smaller wavelength. And we can get diffraction pattern. So one of the diffraction pattern here I have shown, and this is also called as a reciprocal lattice or a Fourier space. And you have seen here, these rays are diffracting or diverting, but this angle is less than 1 degree. Here it is an exaggerated image, but these angles are much smaller. Most of the times they are less than 1 degree. Now, here an important point in TEM is that we don't converge or we don't have a convergence lens. We have only convex lens. So we can just converge electron beam. Okay. So we cannot diverge electron beam. This is an important point. In optical microscope, we can diverge also, but in case of electron microscope, we can only converge electron beams. And here the magnification can be seen as M is equal to B upon U. where V is this distance from the lens to the image plane, and U is the distance from lens to an object plane. So magnification can be written as V upon U, and this image clearly indicates I put my hand towards the light source. That means I have decreased U and I have increased V. So I have increased my magnification here. So it becomes quite intuitive to understand how magnification works in TEM also. And where this diffraction pattern forms, we have seen in an earlier image also that this plane is called as a back focal plane, where you can get a diffraction information about from the sample. And from TEM, we can get both diffraction pattern as well as image. However, we can converge these electron beams. So it is very important to understand that we are not using all the scattered beam. We are just using a part of a scattered beam to form an image. So this is an important point, and that is why the apertures in TEM plays an important role. Now coming to a contrast in TEM, we have amorphous material. Let's consider this amorphous material. And here you can see the thickness is varying in these two cases. So you can see that where the sample is thin, you have more intensity which is coming out. Whereas where sample is thick, you have smaller intensity which is coming out. Now in this case, here the atomic number is higher. So you can see that even the thickness is same, but the intensity which is coming out is smaller. So this kind of contrast which we get is called as a thickness contrast, and this kind of contrast which we get is called as atomic number contrast. So in crystalline materials, what we have a different orientation of atomic planes. When these electrons interact with this kind of grains, they diffract differently, and thus they result in a contrast which we call as a diffraction contrast. We'll be looking at it in more detail as we move along. And there is one more contrast as a phase contrast. Now let's understand this contrast, how it comes. So let's consider a wave nature of electron, and I write this as equation psi is equal to psi naught exponential of IW, where or I omega, where omega is a phase and psi naught is an amplitude. Now, if I change this amplitude or omega, there will be change in this wave nature, and that's create a contrast in a material. So we have contrast here. So I can change this amplitude and I can get an amplitude contrast. I can change a phase, or whether there is a phase change, I will get a phase contrast. In amplitude contrast, what we get is like there is a mass thickness contrast and a diffraction contrast. So when I talk about contrast, I'm talking about a difference in intensities. This has to be understood. So I have, let's say, two pixels which are adjacent to each other and having an intensities I2 and I1, and I can find out the difference between intensities and normalize with one of the pixels intensity, I can get a contrast. So C is equal to delta I upon I1, and intensity like depends on this contrast depends on an intensity also. So if I have a higher intensity, I will have a less contrast. If I have a lower intensity, I will have high contrast. And for your information, like our eyes can tell the difference if contrast is less than 5%. Now coming to mass thickness contrast. So we have seen this. So consider this image, and here you have lower mass thickness. So thickness is lower, so it will not scatter rays as much as this region is scattering. And that is why you will have maximum intensity at this plane, at image plane. Whereas here the electrons are being scattered more. So that is why it loses intensity in transmission mode, and thus you have a lower intensities here. Now based on this image, you can see that if I have more atomic number here, it will scatter more. If I have a lower atomic number, it will scatter less or scatter less. So here, the first case, we have higher Z, which is atomic number. So it causes more scattering, and there will be less intensity in the direct beam. And when you have a thicker samples, thus it also causes a more scattering and results in a less intensity in the direct beam. And we have a very thick sample, just it blocks the beam and there will be no intensity in the direct beam. That is why our sample thickness, when we prepare sample for TEM, they are like 100 to 150 nanometers. So as this beam should not get blocked. So here in this case, it's an image from a book. So you can see that these darker regions are showing a segregation of heavy metals in a polymer. And thus we get this kind of a contrast. I can see a bright region here and a darker region here. Darker region is because these are high atomic number elements which are segregating in this place. So this kind of mass thickness contrast is mostly used by polymer scientists and biologists. Now coming to a mass thickness contrast, and here like I would like to just give an introduction to HADF or ADF detector and bright field detector. So we have a specimen here and we converge a beam in a way where it forms very small spot on the sample, and when it interacts, it creates a signal. So it creates a signal in a forward way, and that is when that will be detected by this bright field detector. We'll be looking at bright field and dark field as we go along. So it is actually on axis detection. That is why it is called as a bright field. Here in this case, if there are elements which has low atomic numbers, they will cause a scattering, and that kind of scattering is called as a Rutherford scattering. So you can look or read about this Rutherford scattering, where the intensity of these beams is directly proportional to the Z square, which is atomic number square. So if I have a lower atomic number, so that will scatter at a lower degrees. So let's say in this range, which is theta 2, which is mentioned here, that is 10 to 50 millirads. When I have an atomic number higher, this will scatter more, that is theta 1 will be 50 millirads. So here I can detect elements which have higher atomic number. Here I can detect elements which have a lower atomic numbers. So that has been done by this ADF, that is annular dark field detector, or HADF, that is high angle annular dark field detectors. So these are nothing but these are annular detectors. That means these are discs with some gap in it. So this is what the openings in the discs are. So that is why they are called as annular detector. High angle means they are at high angles, and thus they are called as a high angle annular dark field. Now, what is an utility of this HADF or HADF detectors? So here you see a classical case where this germanium and silicon are grown on SiO2. Now this germanium and silicon are having the same crystal structure, that is a diamond cubic. So here you cannot distinguish G and Si, but now if I do this HADF detection, and you can see that germanium has higher atomic number, so it looks brighter here because intensity is directly proportional to Z square. That is what we have seen. So germanium will be brighter as compared to silicon, and thus we can differentiate germanium and silicon. That is how we can use HADF detector to find out a composition in a given specimen. So with this, we'll move ahead and talk about diffraction contrast. We talked about mass thickness contrast and diffraction contrast, and these are all amplitude contrast. So here I have shown an image where the electron beam falls and there will be a diffraction phenomena which is occurring. So I consider only a transmitted beam, and that is, I call it as a bright field imaging. When I consider a diffracted beam for my imaging, I consider it as a dark field imaging. We'll be looking at this. Just to give an introduction, I'm talking about diffraction contrast here. Here we can use different apertures to get an image from these diffraction spots and try to get bright field and dark field. So the diffraction contrast is very important to understand dislocation imaging. So here the same features, like same dislocations, are imaged with different as that is an error which we will be discussing in the coming slides. So here I can image dislocations, or I can resolve dislocation in a different way, just changing a diffraction contrast. Now let me come to a phase contrast. So phase contrast can be obtained when I consider two or more beams. In earlier image, I just consider one diffraction spot, but here in this case, if I consider more diffraction spots, I can form an image, and that contributes for a phase contrast. So here, this equation indicates that intensity, you can just see this part, it is proportional, sinusoidally varying with respect to S, which is a deviation parameter, and thickness, T is the thickness of your sample. So let's understand how this lattice fringes forms when I talk about phase contrast. So let's consider these 3 diffraction spots. And when I consider this, I will get a fringes in this pattern. Okay. So when I'm considering these 3 spots, these fringes are perpendicular to this direction. Let us mark that. So here I can consider this as a G, which is a reciprocal lattice vector, and it will be given as 1 upon D, which is nothing but a fringe distance. So this distance is D, and this distance will be 1 upon D. So it is an inversely proportional to a D spacing of these fringes. And how this fringes intensity varies? It varies with a sine function, because here there is a sine function. So intensity varies with a sine function in these fringes. Now let's consider 2 more spots here in this way. So now you can see that these spots were widely spread and these are narrowly spaced. So when I talk about these spots, where will I get fringes? So these spots are in this direction, so fringes will be perpendicular to this direction. So this will be horizontal lines. So these will be the fringes which you obtain from these 2 spots. And you can see these are narrowly spaced. So here these fringes will be widely spaced. Now, what is the utility of this phase contrast? That we can get these lattice fringes from our sample, and we can identify grain boundaries, lattice planes, twins, and interfaces. So this is an utility to get this high resolution TEM images to find out where are the defects, where are the interfaces lying. Now, very important point which I have touched upon in HRTM is that we only get intensity, direction, and B spacing information. So most of the time, people get confused between lattice fringes and lattice planes. So what we see in HRTM images, like images which I have shown earlier, those are lattice fringes. Those are not lattice planes. Thus, the bright spots in those HRTM images are not individual atoms. This is very important point. Or those are not even atomic columns. And there is no direct relation with position of atoms. So this is very important. If someone claims that those are atoms, just walk away from that person. They can talk to a good microscopist. So the important point here I would like to make that lattice fringes are not lattice planes, and whatever spots you see, those are not atoms. So there is another contrast which comes from Moire fringes and Fresnel fringes. So that is also a phase contrast because change in the phase. And that happens when there is a slight shift in the atomic planes. So there is a translation of one atomic plane over another atomic plane, and you see this kind of fringes. If it is rotated, you will get this kind of fringes, and this is a mix. So it is translated as well as rotated. So whenever you see a fringes in TEM micrograph, those are because of the phase contrast. Now let's understand diffraction in terms of vector form. So here, let's consider the incident intensity of electron beam as Ki, and this vector, diffraction vector, is represented by Kd. Now I'm writing in a vector form, so what I can do is that I can put this vector here, Ki, and I can put this vector Kd here. And the angle between them, let's consider it to be 2 theta. And let's consider the resultant of these 2 vectors to be K. Now, as I have mentioned you, this diffraction is an elastic scattering. It happens because of the elastic scattering. So when I say elastic scattering, that means the magnitude of this Ki must be equal to magnitude of Kd. So that is what we have done. So here K, which we have written here as K is equal to Kd minus Ki, which is the resultant K. And the magnitude of this Ki and Kd must be equal because there is an elastic scattering. And we write it as 1 upon lambda, which is a wavelength. And I consider it to be K, mod of K. Now, if you look at this diagram, you can find out what is the sine theta, and it can be given as K by 2 upon Ki. And this K, I can write it as 2 sine theta upon lambda. Now, when you have Bragg's law satisfied, I can write this 2 sine theta upon lambda as 1 upon D. And this 1 upon D is nothing but, I write it as a reciprocal lattice vector, which is nothing but G. So I can say that this resultant KB, when there is a Bragg's law satisfied, I can write it as a reciprocal lattice vector, which is G. And this is a very important result. So let me write it down here, that Bragg's law is necessary condition, but it is not sufficient. Not sufficient. This is very important point here. So what is a sufficient condition? The sufficient condition is this condition. So whenever someone asks you now onwards, what is a Bragg's law, you should tell this relation rather than saying 2d sine theta is equal to n lambda, because this is a necessary and sufficient condition to follow Bragg's law. Now, to go in more detail or to introduce some terminologies, so let's consider these are lattice planes and these are incident electrons and they get diffracted. So this is our reciprocal lattice vector G, and this G is nothing but one of the type of HKL. So let me mark here also, if these are some HKL planes, so this will be, let's say, first HKL, and this will be 2H, 2K, and 2L. And similarly, you go along here and you get 6H, 6K, and 6L. And I denote it to be as G, 2G, 3G, 4G, 5G, and 6G. So these terminologies are important because we'll be using this when we are trying to image dislocations. And in the opposite direction, you can see it as minus G, minus 2G, minus 3G, etc. Now let me introduce an evolved sphere to you. So here, these are reciprocal lattice points. Here I'm talking about a sphere, but we are seeing a 2D projection of these 3D objects. So this sphere is nothing but a circle which I have marked. And here, this Ki and Kd, we defined it as to be 1 upon lambda. So when I construct a sphere here with this radius, I can see that this sphere or this circle is touching or intersecting some of the reciprocal lattice points. And these are the reciprocal lattice points. These are nothing but an individual plane. So you know that in reciprocal space, one point represents one plane. So these planes only will contribute towards the diffraction. So in this case, which are the planes which will be diffracting? So that will be this plane, because the world sphere is intersecting here and maybe here. So you can clearly say that if I reduce lambda, I can increase the radius, and thus I can intersect more number of reciprocal lattice points, which causes a diffraction. Now let me introduce one important term here, which is reciprocal lattice rods. So we see in earlier slide, those were points, but in most of the samples which are thin, in case of TM, those samples are really thin. So these are not points. These will be rods. So here you can see there is a construction of evolved sphere, and these are rail rods. So where this evolved sphere is intersecting, those reciprocal rods will diffract, and you can see its utility as we move along. Here in this case, I have marked a rail rod here, and here a reciprocal lattice point. And we know that from this point to this point is our G vector, which is a reciprocal lattice vector. And you can see that this evolved sphere is touching to the higher side of this rail rod, or opposite upper side of this rail rod, where I consider this as a deviation parameter or excitation error. So you can write, let me write it over here. So you can see that this is G, which is going over here, and this is S. This distance, this is a vector which is S, and I call it as a deviation parameter. Let me write that down also. We'll be looking at it in the coming slide. So this is a deviation parameter, and we'll be seeing why this deviation parameter is so important. So you have got introduced to rail rods and this parameter, this vector, which is a deviation parameter. So when I have a thickness, smaller thickness, I have rail rods to be in this direction, and their magnitude is represented here. When I increase the thickness, the magnitude of these rail rods decreases. So as I go on increasing, these rods will turn into kind of a sphere. So here you can see that if I have thickness smaller, the magnitude of rail rods is higher. If the thickness is higher, the rail rods are smaller. Now let's say if I tilt my sample, and that's what we do in TEM, we tilt this sample, and when there is an evolved sphere which is cutting, now you can see here that this evolved sphere is cutting through some of the railrods. Now, if I want to see that this railrod is not been cut, so this point will not diffract at all. This point will diffract to a maximum intensity. This point will diffract to a lower intensity than this. And here you can see that this as deviation parameter is positive because this sphere is, this point is inside the sphere, evolved sphere. So that's why this deviation parameter is positive, while here the deviation parameter, that is S, is negative. Now, this application of railrods, you can see that the sample will not be a flat, as we see that will be tapered always. And you can see that the beam is interacting with the top surface and the bottom surface. And how does it forms an image in or a diffraction spots? So this surface will create a rail or a diffraction spot here, and this surface will create a diffraction spot here. How this is useful? So let's consider a twin. So you have, you must be knowing twin, and let's consider this as a twin interface. So here in this case, let me mark here. So the railrods will be in this direction, and you can see that there will be streaking which is occurring. So because of the evolved sphere, let us mark an evolved sphere. So evolved sphere, when it passes through like this, so it will cause a streaking in this direction. And that is why we see two spots also because of these regions. So even though there is a twinning, we see these two twin spots. And that is a mark of there is a twinning in the material. So you have a streaking because of this smaller one plane, which is there as a twin interface that causes streaking. And you have this two orientation change, which causes a twin spots here. Now, coming to precipitation and diffraction. So when we have, let's say, a feature which are of cube size, you get railrods in all three directions, that is X, Y, and Z. If you have a sphere, you get shell kind of railrods. If you have disc, you get rod kind of railrods. When you have rod, you get discs and rings. Let's focus on this image now. And you have these precipitates or GP zones in the microstructure. And these precipitates are in this direction. So you get railrods or like streaking in this direction. So the railrod will be in this direction and streaking will be in this direction. And there are some other precipitates which are in this direction. So you get streaking in this direction. So when there is a streaking present in a material or in a micrograph, you can clearly say that there are some fine precipitates and you can find out their locations too. Now coming to a TEM imaging, I'm talking about bright field and dark field. So here I have an optic axis, and here you can see that I'm using forming an image because I'm using a transmitted beam. So here I call it as a bright field. Here there is a diffraction occurring, and I put an aperture here. And you get an image. I call it as a dark field. Now in this third case, what I'm doing is rather than shifting this aperture to a diffracted beam, I'm tilting my beam. So what happens that the diffraction beam passes through this aperture, and this kind of dark field which we get is called as a center dark field. And I recommend that you always go for this kind of center dark field when you want to get bright field or dark field images. So always go for this center dark field because you are not playing with apertures which are aligned properly. So you're not playing with an alignments of the microscope. So go with this kind of center dark field whenever you want to do dark field imaging. Now what is the utility of bright field and dark field? So here there are precipitates which are present, and I get a diffraction pattern. I put an aperture here and I can find out what are the precipitates. So I can clearly identify precipitates just by imaging or putting an aperture at an appropriate diffracted spot. So it's an application of bright field and dark field. Also, you can find out what are the variants of precipitates. So I have a diffraction pattern, and here, let me introduce here. So here, I have used GS110. So I use this diffraction spot and I can identify which are the precipitates which are going to give me this kind of diffraction. I can find out different precipitates, their size, their orientation, just based on bright field and dark field imaging. Similarly, here I can find out what are the shapes and size of precipitates with respect to their spatial resolution also. So you can figure it out what can be the nature of precipitates using this bright field and dark field. Now we are talking about parallel beam diffraction. So here we consider the electron beams are parallel and we form an image or diffraction spot. So we know that this will be the diffraction spot or the diffraction which we get will be limited by selected area diffraction, and we'll be looking at it now. So let's say we have a single crystal. So we get a spotty pattern like this, and this is a selected area aperture which we are using. So if there are 2-3 grains or a polycrystal material, you get a diffraction pattern like this, which is not a continuous but a spotty pattern. And here you have many grains, and we get this kind of a ring pattern in case of microcrystalline material. So based on aperture size, you can have this kind of a diffraction patterns from a material. Now, let's say diffraction from various materials. So in amorphous material, you get amorphous hollow. So this is a typical signature of amorphous material. In microcrystalline material, you get a ring pattern. In polycrystals, you get a pattern like spotty pattern, but it's not continuous. And from a single crystal, you get a spotty pattern like this. Now, important point to note here is that when you have two-phase materials, so here I get some kind of a satellite spots. So you should not consider this satellite spot as something coming from a diffraction. This happens because the electron beam interacts with this phase and then with a matrix, and that is why it creates a satellite spot. So you can read about this satellite spot in more detail from Carter's book. And let me come to the main important point here, which is indexing the diffraction pattern. So to do that, first you should know what is your camera constant. So you have incident beam which interacts with the specimen, and this specifically this planes, and which has a d-spacing, and this is a length of camera, and this is a diffracted spot. And based on this geometry, what you can do is that you get this diffraction pattern, and you find out what is the radius or this r from your transmitted spot to a diffracted spot. Now, if I know this r, and if I use a standard specimen, let's say gold or so, I know the d, I know lambda, I can find out this L. Now, when I configure my microscope using this relation, I can easily find out what are the d spacings just based on measuring this r, which is a distance from a diffracted, from a transmitted spot to a diffracted spot. So first thing, when you want to do diffract or indexing diffraction pattern, make sure that you know what is a camera constant. This lambda, the product is called as a camera constant. And this is a fixed for a fixed microscope. Another important thing is that you must be, when you're doing diffraction, so when you do diffraction at different magnifications, the diffraction pattern will orient or change. So there is a rotation when you go for a higher magnification, and you can correct that rotation based on image. So here, this is molybdenum oxide, which I have shown this edge is 001 plane, and which bears some angle with this diffraction pattern. And based on this relation, you can find out what is a rotation degree, that is rotation of this diffraction pattern with respect to image plane. And this is important to have coherency when you do diffraction analysis at different magnifications. So you get this kind of a relation with a magnification setting and a rotation angle. So this is what I talked about, the calibration of our microscope. Now let's come to indexing of diffraction pattern. So we have this BCC, FCC, and diamond cubic, for which we have this set of rules. We call it as, let me write it down here. So we call it as extinction rules. So you can read about extinction rules. Not all planes will diffract from these crystal structures. So here in this case, let's say in case of BCC, you have h square plus k square plus L square as 2, 4, 6, 8, 10. So here h plus k plus L is equal to even. That time only a diffraction occurs. So there are different extinction rules, and this table is readily available. So you should know which are the planes which are going to diffract or give me a diffraction pattern in TEM. Now, these are the standard diffraction patterns which are available for both BCC and FCC at different zone axes. So you have a zone axis which is here, and what do I mean by zone axis? So if I consider this as a zone axis, all these planes will be parallel to this zone. So that is what zone axis means. So when you index any plane or index any pattern, you always mention about the zone axis. So these standard patterns are always available in the textbook. Now, coming to an indexing pattern, what you should do is you should always know what happens in the real space. So imagine a crystal structure and try to find out how it gives you a diffraction pattern. So here you can use a vector addition. So here in this case, let's say if I have 0, 1, bar 1 and 1, 1, 0, I can add this 2 and get this 1, 2, bar 1. So you can do vector addition. You can calculate angles between planes, and you can find out the cos theta between these two planes also. So this is simple for a simple BCC structure. So this is you should get an idea about despacing from XRD pattern. I'll be dealing with it shortly. And always get the diffraction from the zone axis. What do I mean by zone axis? So your pattern should be symmetric here. It should not be somewhere you are out of the zone. Now let's consider this random pattern. So in this case, if you want to index this, just take a shortest reciprocal points from this diffracted spot or transmitted spot and make it D1 and D2. Just mark this D1 and D2 and find this D1 and D2 from measuring these distances. Then try to find out an XRD pattern, or you may have an XRD database, and try to find out what is the closest match with this D1 and D2. So once you do that, find out an angle theta between these 2 points, reciprocal points, and then cross check. Now, how will you do the cross check? So here the G vector will be marked in a counterclockwise way. Now to cross check, you have these formulas, okay, which are given in this appendix of elements of X-ray diffraction, quality, and stock. So you have different despacing and you have cos phi values. So for a different crystal structure, they are mentioned already. So this is a tedious job, but if the pattern is unknown to you, you have to do these calculations and find out cos phi and D and do iterations to find out final D and cos phi. And once you get that, what you do is like you take a cross product to find out this zone axis. So if you have these 2 J vectors, you do a cross product of them and find out what is a zone axis. If you know 3 vectors, that is G2 and G3 and G1, you can find out zone axis from this relation. This is already mentioned in Carter's book. You can read about them. So this is a general methodology to find out or index any diffraction pattern for any crystal structure. Now, this is an important topic, Kikuchi diffraction. Let me quickly go into it. So let's say consider this as an HKL plane, and let's consider this as an incident beam which falls on it and it gets diffracted here. Now let's consider another incident beam here which gets diffracted, but this gets inelastically diffracted. Inelastic means there is a loss of energy. So there will be a loss of energy here. Now this inelastically scattered wave will go elastic scattering. That means there will be no loss of energy here, and you get diffraction like this. So you get something kind of a high intensity here and a deficient intensity, because in this case you have 2 incidents where one incidence was of inelastic scatter. So there was a loss of energy. So you will have higher intensity in this region, in this line, and you have deficient intensity in this line. And this is what we call as a Kikuchi diffraction. And these are nothing but the loci of all such points, and these are nothing but a cone. When I image that on this image plane, when these cones intersect, this forms a lines, and these are called as Kikuchi lines. Now these lines will help us to identify the location of the planes also, but we'll be looking at it to tilt our sample. So you have a Kikuchi pattern, and for different crystal structure, you have the different Kikuchi pattern, and this can be a roadmap. So I talked about a zone axis. So let's say I have a zone axis 001 here, and I want to move to this zone axis. So how should I move? I should move in this along this Kikuchi line, or I should tilt my sample along this Kikuchi line so that I should reach this 112 zone axis. So this helps us to tilt sample. Now let's look at how it helps to excite some G or HKL planes. Here in this case, you can see that this bright line is going through this transmitted spot, diffracted spot, and this is a transmitted spot. So you can see that this HKL has a higher intensity. Whereas I move this excess intensity line at this point, which is 2H, 2K, and 2L. So you can see that the intensity of this spot has increased. Now I move this Kikuchi line at this point, and I can see that this intensity of the spot has increased. Now let's consider a two-beam condition, which is very important to image dislocations. So the first thing, you get this symmetric pattern. And now if we want to get two beam, now let me explain it to you here. So let's say I consider this 1 and 2 points, which are marked here, 1 and 2 points, and there will be Kikuchi lines also, which you can get it when you converge a beam. Let's say this will be a Kikuchi line here. So when I want to get these two spots only bright, what I do is like I move along this Kikuchi line. There will be a Kikuchi line here, and I move here. So I will end up getting these two diffraction spots brighter. Similarly, if I want this spot and this spot brighter, I move with the Kikuchi line. Let me mark here also. So let's say I want these two spots, this and this spot, to be brighter only. So I will have a Kikuchi line in this direction. So I move along this Kikuchi line to make these spots brighter. Similarly, you can go to different, or you can excite different HKLs just by choosing a proper Kikuchi line. So here the idea is get a symmetric diffraction pattern and move along a proper Kikuchi line to get these spots. Now coming to defects imaging, which is one of the part of this talk. So where Professor Koken, he's the one who has discovered this big beam technique. So you can read his thesis, which is an excellent thesis on understanding defects in crystal lattice. So this is available online also on the library of University of Oxford. You can just go and read this to understand how you can image defects, various defects in crystal. So here I will be talking about dislocation imaging. So let me give an introduction to dislocations, which are here edge dislocations. We have half plane here, and we have dislocation line, which is perpendicular to this plane of this figure. So here is a dislocation line. Here is our dislocation line. So this is an edge dislocation, whereas this is a screw dislocation. And you know that here will be the dislocation line. I call it as U, and the Burgess vector is parallel to this dislocation line. In this case, the Burgess vector was perpendicular to the dislocation line. And there is a third dislocation, which I call it as a mixed dislocation, where Burgess vector makes some angle with dislocation line. So this is our dislocation line, and the Burgess vector makes some angle. Now, very important point which I'm going to tell you, that this Burgess vector remains invariant. Let me write that down also. Invariant means the Burgess vector doesn't change with respect to position of this dislocation. For a given dislocation, the magnitude and the direction of these Burgess vectors remains the same. So this is a very important one when you try to image dislocations. Now in dislocations, the contrast comes. Let's understand how contrast comes. So here we have an edge dislocation, and here there is our incident rays. And here let's plot this intensity, how intensity varies with respect to this dislocation interaction with this electron beam. I consider this I naught to be an initial intensity, IT is like a transmitted intensity. And now when the electron interacts at these planes, so near the core of these planes will satisfy Bragg's law here. or a Bragg's condition here. So these planes will undergo diffraction, and I call it this intensity as ID, which is a diffracted intensity, and I can write this I naught as IT plus ID. Now, if you look at carefully here, you can see that here I have more transmitted intensity as compared to this part, because in this part I have a diffraction occurring. So I get some kind of a dip in intensity, and that creates a contrast. And that is how we can see a dislocation because of the diffraction which is occurring near the core of dislocation, because this region will satisfy Bragg's law or Bragg's condition. So this is called as a diffraction contrast. And let me give analogy with the bent contours. So here we have two regions. In this region, you have diffraction occurring in this way, which contributes to G. We have seen it earlier, what is the meaning of G. And this region will contribute for minus G. And you can have this intensity variation in a bright field and this intensity variation in a dark field. You can consider this analogy with the bent contours where planes are bent and which causes a diffraction, which is a Bragg's diffraction here, which contributes for a G and minus G. And let me tell you about how dislocation line causes a contrast. So let's say you have a beam, you have a sample, and a dislocation line is parallel to this sample. So you will see dislocations like this in a microstructure. If a beam is falling on your sample and a dislocation line makes some angle with this beam, so you see some kind of a contrast in dislocation. So these are all dislocations. You can see bright, dark contrast which are occurring in these dislocations. So here you have some plain contrast, but here you have bright, dark contrast, which are dislocations inclined with this surface. If the dislocation line is parallel to the beam, you will see dislocations like this. So mind you are seeing 2D projections of 3D objects. So you can interpret dislocations or how they are aligned with respect to beam by just looking at the micrographs. Now here I would like you to pay attention. So here we talked about the Kikuchi, here we talked about evolved sphere and a G vector, which is marked here. So here there is no deviation parameter. The S is 0 here. This is G. And this condition is obtained when we go to two beam condition. And let me mark here. So here our Kikuchi line, which goes through it, which goes to the center of the spot where S is equal to 0. So here S is equal to 0. And in this case, what is happening? Let us mark here. So we have Kikuchi line going here, excess Kikuchi line I'm talking about. So here we have excess Kikuchi line. So let's say this is a spot and this is another spot here. So we have excess Kikuchi line, which is closer to the transmitted spot here. And here we have transmitted spot and we have excess Kikuchi line away from this transmitted spot. So this condition we get when the deviation parameter, which we got introduced, is less than 0. And this condition is reached when this deviation parameter is positive, that is greater than 0. Now we'll be looking at these conditions. So we are already in two beam conditions in this case, and we are using this S value to image dislocations. So when S equal to 0, you get dislocations. Yeah, dislocations are visible, but they are not clear. In this case, the dislocations are not visible at all because we go very close to a Bragg condition and the matrix start diffracting, and thus S is less than 0, and this dislocation we cannot image. Here in this case, S is greater than 0, and you can clearly identify dislocations. So when you want to do dislocation imaging, you should always go for a deviation parameter or excitation error to be more than 0. And how you do that? You do that, let's say, let me again mark it over here. So you have a transmitted spot and you have a diffracted spot. You make your Kikuchi line in this away from this spot. So when you do that, you will get this kind of image. So here I have marked two beam condition, and here I have marked a weak beam dark field condition. So here in this case, I can resolve each dislocations properly. So you should not always go for a two beam condition. Rather, you go for weak beam dark field condition to image dislocations. So we have seen this image already, and we have seen that this core of dislocation gives you minus G and plus G. Now, if you use this spot to index or to image dislocation, what you can see that the dislocations are narrower. If you use this minus G spot, you can see that the dislocations are wider here. So really, what are you doing is like you are using strains, you are mapping strains. You are not actually mapping dislocations. You are mapping strains around these dislocations. That is why we get this kind of differences when you talk about G or minus G, or when you use G or minus G to image dislocations. Now, invisibility criteria is used to identify Burgess vector. Here, I would like you to pay attention on these two dislocations, which is E here and D here. So in this first image, you can see these are two dislocations, E and D. And I know what is a crystal structure. So this is for a copper. And I find out what are the different G vectors. I also find out what are different Burgess vector. And what I do is like, I find out the product of this G dot B. So I just take a product of dot product of this G dot B and find out their values. So when G dot B becomes 0, these dislocations will vanish or they will be invisible. So here in this case, that is corresponding to G equal to 200, and this case is corresponding to 1 bar 1 G. So here you can see that the dislocations are vanished here. E and D dislocations are vanished, and that can happen only when they become invisible. So this is the only condition. Let me mark here. So this is the only Burgess vector which gives satisfy this condition. So the Burgess vector which we can identify from this rotation or tilting of samples is half 0, 1, 1 in these two cases. So dislocation will be visible if G dot B is equal to 0, and there will be weak contrast if G dot B is less than 0. So you find out a matrix for your sample, typical G vectors and Burgess vector, find out where they are invisible, and try to tilt your sample accordingly to figure it out what can be the possible Burgess vector of your dislocation. Now, why G dot B makes dislocation invisible? So I have an H dislocation here. This is a Burgess vector and this is a G vector. Now, if this is an electron beam which interacts, and these planes which are close to the core of the dislocation, they satisfy Bragg's condition and they diffract. So you get we have seen this scenario. In this case, if I tilt my sample in such a way that this all beams passes through it, there will be no planes which can give me a diffraction contrast. So here is a G, and this you can see that this B is perpendicular to this G vector, and thus G dot B gives us invisibility criteria when you talk about dislocation imaging. Now I'm going towards weak beam dark field conditions, and here I can see that here is a transmitted beam, and here we are talking about G. And now you can see that this G is inside evolved sphere. This is an evolved sphere, and this G is inside this evolved sphere. That means the excitation inner, or this S, is positive. So I mentioned you that when you want to image a dislocation, S must be positive or greater than 0. And we are going for a G3G condition. That means I have first G spot, this is 2G spot, and this is 3G spot. So you can see here that I have excited this 3G spot as compared to G spot. The intensity of 3G spot is higher than G spot. I will be looking at how we can do that. So here you first get to a diffraction mode, get a symmetric or get to a zone axis, and get a symmetric diffraction pattern like this. Okay, and this cross represents your optic axis. Now tilt to 2 beam condition. So go to 2 beam condition or excite 1G. So what I'm going to do is like I'll make this intensity of this spot more and this spot more only. So you get these 2 spots, brightest spots. So this is our 2 beam condition. Now what you do is like you dark tilt and bring 1G spot to the optic axis. So I'm going to bring this spot to optic axis. So I have brought this spot to optic axis, and now what I do is like I'll excite this 3G. So this is 1G, this is 2G, and this is 3G. So I excite that. So what I do is like I have made the intensity of this 3G spot more and 1G spot less. And now what I do is like I put a objective aperture and I image the dislocation. I come out of the diffraction. This is how I can get a big beam dark field image. So here in this case, the evolved sphere was passing through the first G spot. When I do G3G condition, what is happening exactly? It passes through the transmitted spot and 3G spot. So this G will have positive excitation error, that is S will be positive, and we image dislocation using this spot. So this is on the optic axis, so there will be not be any problem of alignments when I image dislocation using this spot. So here in this case, you can see that when I image dislocations near to this region, I can get a maximum, or the contrast will be much more, though the intensity is less, but the contrast is much more. But if I widen here, I can say that I get intensity of maximum, but I cannot resolve these dislocations. So this is a drawback if you use more area near the core of the dislocation. Now this is a classic case which I would like to discuss when you talk about big dark field imaging, imaging partials and stacking faults. In the first case, you have this G dot P is not equal to 0. So in this case, the both partials will be visible, because for G dot P is 0, then the dislocations will be invisible. In this case, I do that G dot B equal to 0, and I can see only stacking faults with these two partials. I don't have these partials which are left here. And if this G dot B is equal to 1, I can have only one partial which is visible. So using proper G dot B condition, you can find out whether there are partials or stacking faults in between. Now, I am coming to an end of my talk. So this is an important point, which most of the time we don't consider, that is the image force on dislocations. So let's consider this is a surface, and here your dislocation is lying. I mentioned our screw here. This surface will exert some force on this dislocation, and when it exerts, this dislocation can move towards the surface and gets removed from the material, and thus you lose an information. So this may happen when you focus your sample, or you increase the intensity of beam on your sample. So this kind of force can be imaged or can be understood using another dislocation which is opposite of this surface, that is called as image force. I'm not going into details of it, but remember these formulas and try to find out what is a image force acting on your sample. So D is nothing but a distance of your dislocation from the surface of your sample. So you know your material, the Burgess vector, and you know what is the sample thickness, and you can find out what can be the force which is acting. Now, let's say you can compute Nabarro pulse Nabarro stress as G exponential of minus 2 pi W upon B. You can refer any standard physical metallurgy book, and you can get this relation. If this tau Pn, let me write it down also. So if this tau Pn is greater than Fx, then you don't have to worry. You don't have to worry about image force. But if this tau force is less than Fx, that means this force is more than pulse Nabarro stress, and your dislocation can get vanished, or it can come to the surface. So whatever you may be seeing in your sample may not be the dislocations which you are interested in. So there are certain big beam dark field images which I have taken. So you can see the array of dislocations, and you can see they are gliding on some planes, that is 110 plane, and you can see the climb of these dislocations. You can identify glide and climb just based on your big beam dark field images, and you can understand how the partials or super partials can form in case of intermetallics, also using big beam dark field conditions. Now, this is the last slide and the takeaway message from today's talk. So always use center dark field. I have mentioned what is center dark field. So you tilt your beam and make a diffraction spot at the optic center. That is what I mean by center dark field. So always use center dark field. Always take bright field and dark field images with their corresponding diffraction pattern. So now onwards, when you are taking any TM images, always do diffraction. That is very important. The next is for indexing, always take diffraction pattern with the proper zone axis. This makes your life much easier. Always go to proper zone axis, tilt your sample and get to proper zone axis and take a diffraction pattern from there. And that diffraction pattern will be symmetric and that will be very easy to index. You don't have to depend on anyone for indexing such kind of diffraction patterns. For dislocation imaging, this deviation parameter must be greater than 0 or it must be positive. Weak beam dark field condition, this is the best suited G3G condition for any dislocation imaging. And the last but not least, like whatever you are seeing the dislocation, some dislocations may be glissile and thus you have to consider the image force acting on them, and some dislocations may be sessile. So always make sure what kind of dislocations are you looking at. So it is very important to find out a Burgess vector of a dislocation when you are doing a dislocation analysis. And with this, I will stop here. Shruti, over to you.
Thank you so much, sir. This was really very informative. So here are some questions in the chat box. I'll take them up one by one.
Okay, I can read that. Sir, can you please explain the cone formation in Kikuchi pattern? Okay, I can do that. How Kikuchi pattern in EBST in SEM and CPD and TM are different? Let me take first point. So let me so let's say you have a plane here. Okay, so I have a incident beam, electron beam, and it gets diffracted. So let's say it makes an angle theta here. Okay, but this theta can be at any angle. So I'm looking at 2D here. Okay, but if I consider 3D, what will be? It will be like a cone. Okay, so it will be a cone. That is why you get a cone in case of when you consider a 3D case. Okay, and that is why we talk about when you get Kikuchi lines, I consider this as a cone. Is I think with this it is clear, I guess. Then second question is how Kikuchi pattern in EBST, in SEM and CBD in TM are different. When ring pattern and Kikuchi pattern form for polycrystalline material. So Kikuchi patterns are not different in EBST. It just the signals which you get from SEM and SEM and TM. So in SEM you get Kikuchi pattern in a backward direction, while in TM you get Kikuchi patterns in the forward direction. But in both cases, let me explain it to you also here. So let me choose another color. So let's say in TM, you are looking this plane. Okay, so this is TM. But when I talk about SEM, I'm looking about backscattered. So this will be SEM. So this electron will fall and it can reflect back also, which creates a Kikuchi lines here. Okay, so this will be Kikuchi lines in SEM. This will be Kikuchi lines in TM. Both have same phenomena where inelastically scattered electrons will go elastic scattering. So inelastic scattering electrons will go elastic scattering. That is how Kikuchi lines forms. Okay. And when the ring pattern and Kikuchi pattern form for polycrystalline material. So Kikuchi pattern forms for a specific thickness in case of TM. You should not have a very thin sample. If you have very thin samples, you'll not get Kikuchi pattern. You should have some minimum thickness. Okay, like let's say something around 120 or 150 nanometers. If it is less than 100 nanometers or so, you will not get Kikuchi pattern. You will just get a diffraction spot. And when the ring pattern forms, so I have mentioned you the ring pattern is because you have more grains which are diffractive. If you have more grains, so you can say that these grains are oriented in a different way and their loci will create a ring pattern actually. And how to mark G vector on image plane. Okay. Let me draw that also. So you have a diffraction pattern. Let's say I draw this diffraction pattern something like this. Okay. And I have this G vector. This G vector. Okay. And I have mentioned you have to calibrate your microscope. Okay, with rotation with this pattern and image pattern. So let's say you get an image, and you know what is rotation of this diffraction pattern with respect to your image plane. Okay, this rotation you have to find it out for your microscope. It changes with your magnification also, and there is a procedure to do that also. So I have mentioned that in my slide. So you have this G vector. You have this G vector, and when you identify what is this pattern is rotated with this image, you just put it parallel on this image. So let's say there is no rotation here. Let's say there is no rotation in this case. What I do is that I'll just put this mark as a G vector here. That is how you put the G vector on your image. Then so there is a question: reciprocal lattice plane imaged. Explain it, sir. So we use a concept of reciprocal lattice, okay, to understand diffraction better. We can't image it, okay. So we try to use a reciprocal space to explain how diffraction can occur. So basically, real space is only get imaged. Reciprocal space is to assist you to understand how diffraction is occurring. Kindly fill this feedback form. Okay. How is RF different from phase contrast? How can we differentiate if both images are given? So in HardIF, what you have, you will get a Z contrast. Okay. So you read about Rutherford scattering, where let me explain to you. So let's say I have a atom like here, and I have a nucleus. When electron comes very close to the nucleus, it will get I can say scattered. This will be inelastic scattering. Okay, so this electron will get inelastically scattered, and this depends on Z, or the atomic number of this element, and that is how HardIF works. Okay, so more the deflection, more is the atomic number. This is straightforward relation. In phase contrast, what you do is you take different diffracting images also. Okay, so this also comes into mass thickness contrast. But in phase contrast, let's say I have diffracted spots like these here, and I form an image using these two spots. Okay, so I will definitely get a phase contrast, okay, because I'm forming an image from these two images, these two spots. So the concept of phase contrast is a change in the phase. So I have mentioned you this relation, psi equal to psi naught exponential of IW. So if I omega, so this phase is changing, you will get a phase contrast, no matter what. Like if you consider only one spot, you will get a kind of a diffraction contrast. But if you consider many spots, you get a phase contrast. And I think this was the last question.
So we also have Sarvesh, who is raising his hand.
Okay.
Yes.
Yes, Sarvesh, please.
Hello, sir. A very nice presentation. I have not seen any presentation like this on dislocation analysis. Very pragmatically you are presented. So only one question I have is, what was the tilt which you used for your dislocation analysis, alpha and beta tilt?
See, alpha and beta tilt will depend on which kind of a grain are you looking at, or how it is oriented. Okay. So there is no such value for alpha and beta tilt. I also in my PhD days I thought I can calculate some alpha and beta tilt values, but that is a myth. Okay, so you try to go to zone axis and try to tilt it. So if you are very close to zone axis, you can find out what is alpha and beta. Okay,
So you have done variety of materials. So what was the preferable alpha and beta tilts we need to have in the TM for this type of dislocation analysis? Yes, of course, if the it depends upon the orientation of the grain and the dislocation I'm trying to capture. But if you see if some TM is capable or not, how to decide that, okay, this alpha and beta tilt, with this alpha and beta tilt I can do dislocation analysis in this TM.
That is a very tricky question because as far as I know, you don't have to go more than 10 degrees in beta tilt, and you don't have to go more than 30 degrees in alpha tilt. If you can't image that between these ranges, it is unlikely that you have dislocations. Like, you can image it.
Okay.
Okay. So, and it depends on a goniometer also. So if you have TMs which goes which has goniometers like plus 30, minus 30, those kind of TMs are useful for dislocation imaging. You go for HRTM and all, they don't have proper tilt. Okay, so you can't tilt your sample much. Okay, so those have tilt less than 10 degrees also. Okay. So yes, if you are not able to do that, I think there is less chance you can image it. Okay. And one more important thing here, when you tilt your sample, do not do not focus your sample electronically. What do I mean by that? There is a knob, and you try to focus it. So basically, you are disturbing the alignment.
Yes, dislocation also will start moving.
Yes. So basically, what you do is like you adjust the height. You move your sample in a eccentric height. So you use a Z height and try to adjust the focus, or try to focus the image.
Okay. Thank you, sir.
Yeah, thank you, Saresh. So here,
Another question.
Alok is asking, he has an amorphous phase. Is there any possibility to change amorphous phase to crystalline during the sample preparation, like ion milling? Yes, definitely. You have probability if your amorphous phase is very fragile, so it can change to crystalline also. I have seen that happens even if you put it in TM also. So if you have amorphous phase and you try to put it in TM, and then you try to focus your sample, and if the intensity is too high, the amorphous phase can change into crystalline. So yes, there is this chance. Basically, most of the time you should not focus your sample, because you read about this beam damages. So in beam damages, like even crystalline samples can get damaged. So yes, amorphous phase can get crystalline also. So basically, if you are amorphous material, try to do ion milling at very low angles and at lower electron volts. That energy, lower electron energies. So maybe Dr. Bhagyaraj is talking tomorrow, so you can ask this question to him, how to prepare an amorphous sample using ion milling or pips.
Are there any more questions from the audience? I guess there are no more questions now. I would like to thank you once again We also had Balani sir for the entire talk. Sir, if you can please say something.
No, I think it was also good learning for me. I also, I think, learned multiple new things about G being, inside or outside that particular Ward sphere, or what else to do in terms of, mapping your, I think, dislocations as well as stacking faults. The width also changes. So multiple things are also new to me. So it was very good to learn so much from Dr. Chawake. Thanks.
Thank you, Professor Balani. Thank you for giving this opportunity.
Thank you so much, sir. So we also have a session scheduled tomorrow, sample preparation by Dr. Bhagiraj. So kindly join tomorrow as well. Thank you so much, sir, for this really very informative session. Thank you, sir.
Thank you, Shweta. Thanks a lot.
I request the audience to please fill the feedback form if they need the recording of this session. The feedback form will be taken up as your attendance for the session.